Color vision. Introduction. Color vision is the ability of the eye to identify different colors. Human eye can recognize about 150 colors. Color perception depends on cone cells in the retina. Visible spectrum. Spectral colors. White light passing through a prism split into colors. This band of colors is called visible spectrum. Colors are called spectral colors. Spectral colors are red, blue, violet, orange, green, yellow, indigo. Wavelength. Red has the longest wavelength, approximate of 8000 nanometer. Violet has the shortest wavelength, approximate 3000 nanometer. Infrared and ultraviolet rays. Rays longer than red are infrared rays. Rays shorter than violet are ultraviolet rays. These rays do not produce vision. Refraction. Red light is refracted least. Violet light is refracted most. Longer wavelength leads to lesser refraction. Bunchkin phenomena. It is the shift of brightest color in spectrum when illumination changes. In bright light, yellow appears brightest. In dim light or true light, green appears brightest. Also called Vission shift or Vission effect. Cause: cones response maximum to yellow, rod response maximal to green. Spectral colors. Colors not present in visible spectrum formed by mixing two or more spectral colors. Example, purple is equal to violet plus red. Pink is equal to red plus white. Primary colors, colors that combines to form white light. Primary colors are red, green, blue. Complementary colors, pair of colors that produce white when mixed properly. Example, red plus greenish blue, orange plus can blue, yellow plus indigo blue, violet plus greenish yellow, purple plus green. Theories of color vision. Thomas Young trichromatic theory, proposed by Thomas Young. Retina has 3 types of cones. Each cone responds to one primary color, red, green, blue. Different colors are produced by combined stimulation of these cones. Equal stimulation of all 3 cones produce white color. Trichromatic theory, proposed by Helmholtz, also called Young-Helmholtz theory. Sensitive optic nerve fiber responds selectively to red, green, blue. Different color sensation occurs by varying stimulation of these nerve fibers. Grantin-dominator modulary theory, proposed by Granit, based on activity of retinal ganglionic cell. Ganglionic cell respond to the whole visual spectrum. Ganglionic cells are divided into dominatory and modulator. Dominatory, responsible for brightest or intensive of light. And two types, condominator, active in light, adopted eye, maximum response around 550 nanometer, rod diameter, active in dark, adapted eye, maximum response around 500 nanometer. Modulator, responsible for color sensation. Three type, blue modulator, response to 450 to 470 nanometer. Green modulatory, responsible to 520 to 540 nanometer. Red yellow modulator, response to 580 to 600 nanometer. Example, green light stimulates green modulator more strongly. Heterogeneous polychromatic theory. Retina contains 7 types of receptors. Receptors are arranged into 3 units. First unit, tricolor unit, receptor for orange, green, blue. Second unit, dye unit, dicolor unit, receptor for yellow, blue. Yellow and blue are complementary colors. Third unit, dicolor unit, receptor for red, blue, blue, green. Herring theory of opposite colors. Retina contains 3 photochemical substances. Each substance gives color sensation by breakdown or resynthesis. First substance, white-black substance, breakdown, white sensation. Resynthesis, black sensation. Second substance, yellow-blue substance, breakdown, yellow sensation, resynthesis of blue sensation. Third substance, red-green substance, breakdown, red sensation, resynthesis of green sensation. Importance, explains successive contrast after images, does not explain simultaneous sensation of opposite color. Color sensatory area of retina. Peripheral retina has no cones. Peripheral retina is insensitive to colors. Peripheral retina gives sensation of white, black, gray. Fovea centrale has maximum cones. Fovea is highly sensitive to colors. Extrafovea region contains both rod and cones. Size of color sensitive area. Blue sensitive area is the largest. Green sensitive area is the smallest. Red sensitive area is next to blue. Yellow sensitive area comes after red. Color area of retina are mapped using a perimeter. So size of color sensitive area. Blue sensation area is the largest. Green sensitive area is the smallest. Red sensitive area is next to blue. Yellow sensitive area comes after red. Color area of retina are mapped using perimeter. Contrast effects. Simultaneous contrast. Contrast between two adjacent colors becomes intensified. Black appears blacker against white. White appears whiter against black. Green appears brighter against red. Red appears brighter against green. Maximum effect occurs with complementary colors. Cause simultaneous of one retinal area affects neighboring area. Sensitive to surrounding colors increases. Horizontal cells are responsible. Successive contrast previously seen color affects periconception of next color. Example, after viewing bright red, green appears more greenish. Causes: previous retinal stimulation alters sensitive to next stimulation. Sensitive to complementary color increases. After image, presumption of image after removal of light stimulates. Image remains briefly after closing eye, gradually fades away. Type of after image: positive after image, seen after closing eyes or looking at dark background. After image appears bright, same color as original object. Negative after image, seen when looking at bright or white background. After image appears in complementary colors. Cause of negative after image: perception of retinal activity after stimulatory stops. Color blindness. Definition: color blindness is the inability to appreciate one or more color. It is better called deficiency of color vision. Common in 8% of male, 0.4% of females. Usually inherited as a sex-linked resensitive trial. Can also occur due to acquired disease or injuries. Total color blindness is very rare. Color blind person do not always see only black and white. Causes of acquired color blindness: trauma, injury to eye due to accidents, stroke, chronic diseases, glaucoma, macular degeneration, retinitis, sickle cell anemia, leukemia, diabetes mellitus, liver diseases, Parkinsonism disease, Alzheimer disease, multiple sclerosis, drugs, antibodies, antihypertensive drugs, anti-tuberculosis drugs, barbiturates, drugs for physiatric and neurological disorders. Toxins, fertilizers, carbon monoxide, carbon diffusion, leads, contamination, chemicals, alcoholism. Chronic alcoholism may cause color blindness. Aging occurs after 60 years due to age-related eye changes. Classification of color blindness: monochromatism, total inability to perceive colors, also called total color blindness. Achromatopsia, vision is only in black, white, shades of gray. Types: rod monochromatism. Cones are non-functional. Vision depends only on rods. Person is totally colorblind. Visual acuity is reduced. Flora vision absent. Central zygomatic occurs. Cone chromatism. Vision depends on only one type of cone. Central scotomatic absent. Dichromatism. Person can appreciate only two colors. One type of cone receptor is defected. Person is called dichromatic. Types: protanope, defect in red receptor. Red color cannot be appreciated. Red is confused with green. Uses blue and green for color matching. Dipyrambic, defect in green receptor. Green color cannot be appreciated. Use blue and red for matching. Tritanopic, defect in blue receptor. Blue color cannot be appreciated. Uses red and green for matching. Trichromatism, all three colors are preserved. Intensity of one primary color is weak. Person is called trichromat. Type protanormal. Weak prescription of red, requires strong red intensity. Tetrandrobal, weak prescription of green. Tritanormal, weak prescription of blue. Thank you.